We're going to move a step further in our consideration of partition functions by looking at molecules, not just atoms that might be translating in space, but molecules that can rotate and vibrate as well. So I'll remind you that when we were looking at developing the system partition function, we were writing down the total energy of the system, and maybe I should write a capital E for that, as equal to the contributions from all of the molecules in the system added together up to n molecules or n particles. And that led us to a expression for the system partition function that looked like this, where this z to the n really reflects z1 times z2 times z3 times all the way up to zn. In other words, we've just taken the same partition function for a molecule and multiplied it together n times to get that z to the n factor, and then we corrected for indistinguishability by dividing by n factorial. What we want to do now is something very similar, where we're going to take the sum of a bunch of energies and turn it into a product of partition functions. So in this case, though, we're going to be writing that the energy of a molecule comes from several different contributions. For example, it includes an electronic contribution, it includes a vibrational contribution, it includes a rotational contribution, and a translational contribution. So we're going to have all of these different elements at play in a molecular partition function. So when I write an expression like this for the molecular partition function as a summation over all of the states, okay, and this is just our generic expression for that partition function, I'm now going to write this molecular energy in terms of all of these different pieces. I'm also going to write this summation over states by summing over the actual quantum numbers that each of these energy levels might represent. So for example, I'm going to include a summation over the electronic energy levels. So I'll just label that up here as electronic energy levels. I'm going to sum over the various vibrational energy levels, so that's vib up here. I'm going to sum over the various rotational energy levels, or rotational states, I guess I should say. And I'm going to sum over the various translational states up here. And my element in the integral is simply going to be the sum of all of these contributions. Electronic energy plus vibrational energy plus rotational energy plus translational energy divided by kBt. Now we know that we can take this exponential and write it out as the product of individual exponentials. So for example, e to the electronic over kBt times another exponential, e to the minus e vibrational over kBt, and so forth. I'm not going to write it all out. So that means that I can now write this molecular partition function in the following way. I've got a summation over all the electronic states, so that's just going to be e to the minus e electronic over kBt. And I've got a summation over all of the vibrational states, and I'm going to, so that's vibrational, so I'm going to write this as e to the minus e vibrational over kBt. Now I haven't put an index on these energies that I put in the exponential, but you can assume that the various states are summing over all the possible energies that might be available to that particular component. Okay, for rotation, I'm going to have a series, actually I have more than one rotational quantum number typically. I'm just going to list the one here, e to the minus e rotation over kBt, and another one for translation, which has the three nx, ny, and z quantum numbers for translation, but will be written simply as e to the minus e trans over kBt. So I hope you don't mind my shorthand here, not explicitly listing the quantum numbers as parts of these energies, but I wanted to make the notation a little bit simpler. Now what I'm going to do is basically associate these terms with something I'll term an electronic partition function. These terms will give rise to a vibrational partition function. These terms will give rise to a rotational partition function. And these will give rise to the translational partition function. Now we've already determined what the translational partition function is in this case, and it's going to have exactly the same functional form for a molecule as it had for atoms or any other particle. It's just basically going to be 2 pi m kBt over h squared, all of this raised to the 3/2 power multiplied by the volume. And so this has the same form for all particles. The one thing that will differ for those particles is the mass. So as the mass gets lighter or heavier, it's going to change the relative magnitude of the translational partition function. It's these other three, the electronic, the vibrational, and the rotational parts of the partition function, that we're going to be concerned with in this lesson. Now I'll simply close by saying that for the molecule then, I can write this simply as the product of these various partition function contributions. I should probably say one last thing too, and that is this separation into vibration, rotation, translation, and electronic is actually an artificial separation. I don't mean to say that this is a bad estimation or a bad approximation, just that if we were at sufficiently high energies, we would find that you couldn't really definitively separate vibrations from rotations, and you couldn't separate them from the electronic degrees of freedom either. The only ones that seem to be relatively separable are the translational degrees of freedom, interestingly enough. So although we can formally write down this expression for the molecular partition function, I just want you to know that it is in fact a simplification of a real situation that's actually somewhat more complicated and frankly somewhat more interesting.